Dear students, we are now already in week 10 and we are going to start with lecture 5. During this week, we are going to study chapter 5, Mathematics of Finance. Finance is related to money. So throughout this chapter, you will find that this chapter is a very interesting chapter. We are going to cover 3 of the sections of this chapter. Section 5.1, Compound Interest, 5.2, Present Value, and 5.3, Interest Compounded Continuously. Let us start with the first sections, 5.1, Compound Interest. Compound Interest. Suppose that a principal of P dollars is deposited at an interest rate R per year. Principal P means the investment, which is the initial amount of money a person put or deposit in a bank. Usually, when a person deposits his or her own money in the bank, this person expects the money to grow. Now, let us calculate how the money grows in the first year. Let us see the box below. Number 1. At t equal to 1, S1 equal to P plus PR. T means here is the number of year. So t equal to 1 means in the first year. S1 means the amount of money after 1 year. So S1 equal to the principal plus the interest. The interest here is calculated as P multiple with R. So S1 equal to P plus P multiple with R. So we factor this expression, we will have S1 equal to P multiple with 1 plus R. So this is the amount of money after 1 year. Now let us calculate the money in the second year. At t equal to 2, S2 equal to S1 plus S1 multiple with R. So S1 here is the principal in the second year. And we substitute S1 with P multiple with 1 plus R, we will have P multiple with 1 plus R plus P multiple with 1 plus R multiple with R. So we will have the end result of S2 as P multiple with 1 plus R to the degree of 2. So in the second year, S2, which is the amount of money in the second year, is equal to P multiple with 1 plus R to the degree of 2. Now let's see in the third year. At equal to 3, S3 equal to S2 plus S2 multiple with R. So this is similar way as what we have done in the second and in the first year. So S2 here is the principal in the third year. S3 equal to S2 plus S2 multiple with R. S2 multiple with R is the interest in the third year. So after we do some calculation here, we will get the end result of S3 is P equal to S3 equal to P multiple with 1 plus R to the degree of 3. So we will see the pattern here. In the first year, 1 plus R is to the degree of 1. In the second year, 1 plus R is to the degree of 2. And in the third year, 1 plus R to the degree of 3. Now we can see the amount of money in the fourth year is also you'll have the same pattern. So S4 is going to be P1 plus R to the degree of 4 and so on and so forth. So at T equal to T, so whatever T is will be, so ST is equal to P1 plus R to the degree of T. So at T equal to T, ST equal to P 1 plus R to degree of T. This is in the year of T. Now we are going to generalize the formula. Compound amount S at the end of T, at the end of T years, at the annual rate of R is given by S equal to P multiple with 1 plus R to the degree of T. Compound amount S means the amount after T years. Okay, now we have already the formula of the amount of money after T years we call compound amount. We have calculated previously that compound amount after 3 years at annual rate R is equal to S equal to P multiplied with 1 plus R to the power of T. Here, R is the interest rate which is calculated once a year. However, the interest can be compounded more than once per year. It means can be 2 times, 4 times, 6 times, depending on the policy of the bank. Common compounding periods include semi-annually, 2 periods per year. It means the interest is calculated twice a year. Quarterly, 4 periods per year. It means the interest is calculated 4 times a year. Monthly, 12 periods per year. Weekly, 52 periods per year. Daily, usually 365 periods per year, or continuously. Continuously here means that the number of periods per year goes to infinity. So here the symbol of the number of periods per year is K, so K goes to infinity. Since the number of the interest rate per period is the interest rate per year is R, so it means the interest rate per period will be different number. So if we change the symbol of R become I, which is the interest rate per period, so I is equal to R over K. So now the T, the number of years, is not become the T anymore because now it is become the number of compounding periods. So if we put the symbol as N, so N is equal to the number of years multiple the number of periods in a year, which is K times T. So the next following formula can be derived in the same way as the previous formula. So we substitute the value of R become I, which is I equal to R over K, and N is equal to KT. Now, with the interest rate per period equal to I and the number of compounding periods equal to N, then the formula of compound amount S at the end of N interest periods at the periodic rate of I is given by S equal to P multiplied with 1 plus I degree N. So here is the definition of the variables. I is equal to R over K and N is equal to K multiplied with T. You know that R is the annual interest rate or nominal rate per year. So it means the rate per year. And K is the number of periods the interest is compounded per year. And T, you know that this is the number of years. P is the principal and S is the compound amount. So now you know how to calculate the compound amount S at the end of an interest period at the periodic rate of I, which is S equal to P multiple with 1 plus I to the degree of n. Now, we can finally conclude that, in general, the compound amount S of a principal P at the end of T years at the rate of R compounded K times a year is given by S equal to P multiplied with 1 plus R over K to the degree of KT. Here, we substitute the value of I with R over K, and we substitute the value of n with K multiplied with T. We can see here that we have 5 variables. Variable S, P, R, K, and T. S is compound amount or the future value. P is the principal or the investment or the present value. R is the interest rate, the annual rate or the nominal rate. K is the number of periods the interest is compounded per year, meaning K is the number of times the interest is calculated in a year. T is the number of years. So when we have five variables here, it means when 4 of the variables are given, then we can find the other variables. So we see here that this is the recommended formula to be used for a direct solutions. From now on, we can use this formula to solve the problems. We can rely on this formula to solve for the future problems. Now, we calculate the compound interest. Compound interest is the difference between compound amount S and the principal P. So, compound interest is equal to S minus P. Let us calculate the compound amount and compound interest with different value of K. Suppose $5,000 is invested for 5 years at the rate of 4.5% compounded annually, semi-annually, quarterly, monthly, weekly, and daily. Compounded annually means the interest is compounded once a year, so K equal to 1. Semi-annually means the interest is compounded twice a year, so it's K equal to 2. Compounded quarterly means the interest is compounded 4 times a year, so K equal to 4. Monthly, K equal to 12. Weekly, K equal to 52. And daily, K equal to 365. Now, we substitute the value of P equal to 5,000, T equal to 5, R equal to 0.045 into the formula. S equal to P multiplied with 1 plus R over K to the degree of KT into each of the K. So with K equal to 1, so we found that compound amount S equal to 6,230.91 with the compound interest S minus P equal to 1,230.91. So we calculate one by one with K equal to 1, K equal to 2, K equal to 4, K equal to 12, K equal to 52, and K equal to 365. We found here that the compound amount with different value of K is also different. When we found here, the higher the value of K with the same amount of principal, so the higher the value of compound amount S. So, that's the compound interest. Example 1. Compound interest. Suppose $500 amounted to $588.38 in a saving account after 3 years. If interest was compounded semi-annually, find the nominal rate of interest compounded semi-annually that was earned by the money. Here, we summarize the value of the information. Example 1. Compound interest. Suppose $500 amounted to $588.38 in a saving account after 3 years. If interest was compounded semi-annually, find the nominal rate of interest compounded semi-annually that was earned by the money. From the first sentence, we get three of the variables. Variable P equal to 500, variable S equal to 588.38, and variable T equal to 3. In the next sentence, we have the next variable, which is the variable K, if interest was compounded semi-annually. It means K equal to 2. Find the nominal rate of interest. Find R. So now we have all the 5 variables, which one variable is unknown. We are going to find the value of R here. We use the formula that we have before, the formula of compound amount. S equal to P multiple with 1 plus R over K to the degree of KT. We substitute each of the value. S equal to 588.38, P is 500, K equal to 2, and T is equal to 3. So we have 588.38 equal to 500 multiplied with 1 plus R over 2 to the degree of 2 multiplied with 3. We divided both sides with 500, so we will have 588.38 divided by 500 equal to 1 plus R over 2 to the degree of 6. So from here, we calculate and we end up with the value of R equal to 0.0550. So for the value of the interest rate, we try to have at least 4 or 5 decimal. So 0.0550. To change this into the percentage, we multiply with 100. So we will have R equal to 5.5%. So the nominal rate was 5.5%, compounded semi-annually. Example 2. Doubling money. At what nominal rate of interest, compounded yearly, will money double in 8 years? To solve these problems, we need to get information of all the variables that we need by seeing closely the sentence word per word. At what nominal rate of interest? Meaning the question is what is R? Compounded yearly. It means K equal to 1. Will money double? Money is double. It means from P become to P, because the first money, the first investment is P. If the first investment is P, so this is become to P. So P equal to P and S equal to 2P in 8 years. So T equal to 8. So we have again now 4 of the variables. S equal to 2P, P equal to P, T equal to 8, and K equal to 1. What is R? Again, we have the same question as what we did in example 1. So we use the same formula, S equal to P multiplied with 1 plus R over K to the degree of KT. So we substitute S with 2P, P is P, and K equal to 1, and T with 8. So 2P equal to P multiplied with 1 plus R over 1 to the degree of 1 multiplied with 8. So we have P cancel out, P cancel with P, so we have 2 equal to 1 plus R to the degree of 8. We solve this equation for R, so we have R is about 0.0905. So R equal to 9.05%. So the nominal rate is R equal to 9.05% compounded yearly. Example 3. Compound interest. How long will it take for $600 to amount to $900 at an annual rate of 6% compounded quarterly? From the problems, we get the information of the value of P equal to 600, S equal to 900, R equal to 6%, which is equal to 0.06, and K equal to 4 because compounded quarterly. The only variable that's missing here is variable T, and the question is how long will it take? It means what is T? Since we have 4 of the variables out of 5 variables, we substitute all these variables into the formula. The formula that we are going to use is the same as the formula that we have used before. S equal to P multiplied with 1 plus R over K to the degree of KT. So we substitute the value of S, P, R, and K into the formula. So the remaining only, we don't know what is the value of T. So the problems here, the formula here become 900 equal to 600 multiplied with 1 plus 0.06 divided by 4 to the degree of 4t. We divided both sides with 600, so we have 900 divided by 600 equal to 1.015 to the degree of 40. We simplify so that we have 3 over 2 equal to 1.015 to the degree of 40. Now, we see here the remaining equation is nothing but the exponential equation. 3 over 2 equal to 1.015 to the degree of 40 exponential equation with the variable t. So, previously in chapter 4, we know that when we want to solve the exponential equation, we need to change to become logarithmic equations. Now, when we multiply both sides with length, so we will have length 3 over 2 equal to length 1.015 to the degree of 40. So 40 will go down to the back of length. So we have length 3 over 2 equal to 40 length 1.015. So 40 is equal to length 3 over 2 divided by length 1.015. So we have 40 is equal to 27, about to 27.233. So T equal to 6.8083. So we have here now the value of T. So it will take about 6.8083 years, which is equal to 6 years and 9.5 months. Effective rate. The effective rate RE that is equivalent to a nominal rate of R compounded K times a year is given by RE is equal to 1 plus R over K to the degree of K minus 1. What is effective rate? Effective rate is an actual rate which is calculated based on various values of k, which is the number of periods the interest is calculated per year. So k can be any number, any integer numbers, 1, 2, 4, 12, or any numbers, while interest rate or annual rate is the annual rate when k only equal to 1. So that is the difference between the effective rate and annual rate. So annual rate is only specifically when k equal to 1, while RE, k can be any number. So when k equal to 1, actually the effective rate RE is equal to the annual rate R. So now what is the use of this effective rate? So effective rate or actual rate is usually used to choose a desirable options when some alternative rates are offered. In other words, if you want to choose what is the better or the best choice, so we can use this calculation of effective rate. When the effective rate RE is known or given or asked in the problems, and the value of k is not available, the compound amount formula can be written as S equal to P multiplied with 1 plus RE to the degree of T. This formula is derived from the compound amount formula that we have previously. S equal to P multiplied with 1 plus R over K to the degree of KT. By separating the exponent KT and adding the equation with 1 and minus 1, so you know that 1 minus 1 is 0, so it's not going to change the value of the equations. So we will have S equal to big brackets 1 plus R over K to the degree of K plus 1 minus 1. Move 1 to the front, so we will have S equal to P bracket 1 plus R over K to the degree of K minus 1, all of them to the degree of T. So we know that 1 plus R over K degree K minus 1 is RE. So we substitute 1 plus R over K to the degree of K minus 1 with RE. We have the new formula S equal to P 1 plus RE to the degree of T. Example 4. Effective rate. What effective rate is equivalent to a nominal rate of 6% compounded A. semi-annually, B. quarterly? From the problems, we get the information about nominal rate R equal to 6% equal to 0.06 and the value of K. K equal to 2 when compounded semi-annually and k equal to 4 when compounded quarterly. Number A. Compounded semi-annually, k equal to 2. We use the formula of effective rate that we have previously. RE is equal to 1 plus R over k to the degree of k minus 1. We substitute the value of R equal to 0.06 and the value of k equal to 2. So RE is equal to 1 plus 0.06 over 2 to the degree of 2 minus 1. So RE is about 0.0609, which is equal to 6.09%. So the effective rate, which is equivalent to a nominal rate of 6%, compounded semi-annually, is equal to 6.09%. Number B. Compounded quarterly, k equal to 4. So we use the same formula for RE. RE is equal to 1 plus R over k to the degree of k minus 1. So we substitute the value of r equal to 0.06 and k equal to 4. So Re is equal to 1 plus 0.06 over 4 to the degree of 4 minus 1. So we have Re is about 0.0614, which is equal to 6.14%. So the effective rate that is equivalent to a nominal rate of 6% compounded quarterly is equal to 6.14%. From these two problems, A and B, we found that when k equal to 2, the effective rate is 6.09, which is smaller than when k equal to 4, which is 6.14%. So it means the higher the value of k with the similar value of nominal rate r, so thus the higher the effective rate. Example 5. Effective rate. To what amount will $12,000 accumulate in 15 years if it is invested at an effective rate of 5%? From the problems, we get the information of the value of P, which is 12,000, and T equal to 15. The next variables that we know is RE, which is the effective rate, 5%, 0.05. So now here, effective rate is given. And we can see that the value of K, which is the number of periods that interest is calculated in a year, is not given. So from these three variables P, T, and RE, so what is S? Because the question is to what amount will. So it means the future value, which is S. So in this case, we are going to use the formula of S, which is equal to P multiplied with 1 plus RE to the degree of T. So S equal to 12,000 multiplied with 1 plus 0.05 to the degree of 15. So we have S equal to $24,947.14. The last example of this section is example 7, comparing effective rates. If an investor has a choice of investing money at 6% compounded daily or 6.1 over 8% compounded quarterly, which is the better choice? Since there are more than one option available, effective rate can be used to determine the better choice. For the investor, the higher rate will be the better choice, because the higher the rate, the more the amount of future value will be. So we are going to use effective rate to compare this investment. Option number 1, R equal to 6% and compounded daily. So it means K equal to 365. While option number 2 is R equal to 6.1 over 8% and compounded quarterly, which is K equal to 4. So for option number 1, using the formula of effective rate, RE equal to 1 plus R over K to the degree of K minus 1, we get the effective rate is equal to 6.018% for option number 1. So for option number 2, with the formula of RE2 equal to 1 plus R over K to the degree of K minus 1, so we substitute all the variable here, R equal to 0.0615, which is equal to 6.1 6.1 over 8%, and K equal to 4, so we get RE2 is equal to 6.027%. We compare these two values, RE1 and RE2. We found that RE2, which is the second option, is bigger than RE1, which is the option number 1. So the effective rate of the second option is bigger than the effective rate of the first option. So because of that, of course, the investor will choose option number 2. So option number 2 is quarterly, compounded quarterly, and with the nominal rate 6 1/8% is the better choice for the investor.